So now that you have learned how to calculate double integrals, it's time we think about what's the physical interpretation of double integrals. And for that, I actually want to go one step back and talk about the physical interpretation of single integrals, okay? And the reason I'm doing this is that it's often a bit misleading to think of single integrals simply as the area under a curve, because this intuition about single integrals being the area under a curve confuses you a little bit, because a single integral integrates along a single variable. So why are we getting an area if we're integrating along a single variable? So let me give you a different, and in my opinion, more physically accurate interpretation of a single integral. So a single integral is a way of adding things up along a single variable, okay? For example, imagine you want to calculate the length of a rod. So the way you can calculate the length of a rod is you have your rod here. Let's say this is a one-dimensional rod, okay? Let's assume that the cross-section is 0. It's perfectly one-dimensional. And we define an axis x that goes through this rod. So we are changing between x equals a and x equals b. So now what you could say is that you could divide this rod into tiny pieces, right? For example, a tiny piece could be here. And this tiny piece has a length dx. And by calling this dx, what I mean is that this tiny piece is tending to 0. But then by adding the length of those infinitely small pieces, I can get back the total length of the rod. So the length of the rod is the addition, which is an integral of these tiny differentials dx between x equals a and x equals b. And indeed, if you evaluate this integral, what do you get? The integral of dx is simply equal to x evaluated between a and b, which is equal to b minus a, which is indeed the length of this rod, okay? So notice how the single integral is adding differentials along a single variable. This example was clearly very silly, because to calculate the length of a rod, you just do b minus a, and that's the length. You don't have to do an integral. But it helps you understand what an integral is. For example, imagine that now instead of the length, we want to calculate the mass of the rod, the total mass. But now, so you could say, okay, let's get the length and multiply it by the density. That's true as long as the density is constant. But what if the density is a function that depends on x? So we have a density lambda which depends on x. What happens then? So then what happens is that your total mass will be, let me first draw the rod along the x-axis between x equals a and x equals b. So now what we can say is that we divide the rod again into differential pieces, and each of these pieces will have a differential mass. Let's call it dm, okay? So the total mass of this rod is going to be the integral of dm between a and b. And once again, here you see that an integral is just adding up an infinite amount of infinitely small pieces, okay? Now, what is dm? So dm is the mass of a differential piece of length dx, okay? So you could say that dm, which is measured in kilograms, for example, is equal to the density of this rod, which is measured in kilogram per meter. So this is a linear density, okay? This is how much does this rod weigh per unit length, okay? But this value is changing along the rod at every point. So you cannot simply multiply the density times the length, because it's changing along the length. That's why you need to do an integral. The density, once you multiply it by dx, which is the length, you can calculate the total mass, okay? So the advantage of the integral is that when the pieces are infinitely small, you can say that the mass is equal to the density times the length, because the length is so small that the density cannot change in that small length. So you can treat the mass as the density times the length, okay? So when you substitute this back into the integral, you get the integral from a to b of the density, which is a function of x, with respect to x. And this will indeed give you the mass of the rod. Okay? So that is the key. Integrals are useful when you want to add up lots of things along one dimension, and these things depend on the position, such as, for example, the density. Okay? So you want to add all those up. So now this concept can be moved into two-dimensional or into double integrals. Okay? So in double integrals, you can also use a double integral to calculate the area of a plate. And this is a very silly application, similarly to before, but I think it's useful for you to understand. So imagine you have a plate, a two-dimensional plate. Let's imagine it's infinitely thin. Okay, and here we have defined two axes, let's say x and y. So this plate goes between x, a certain a and b, and y goes between c and d. And we want to calculate the total area of the plate. So what you can do is you say, okay, I split the plate into tiny squares with an area dA, which is equal to dx times dy, which is the step in x times the step in y. Okay? So therefore, the total area of the plate is going to be the double integral of these tiny areas dA. So we are going to add up all these dAs to find the total A. Notice that there is a general trend. When you have a differential inside of an integral, the outside is just the non-differential part. So if this was a differential of an area, the outside is going to be an area. So you now write this as dx times dy. You add the limits, x goes from a to b to c to d. And the end result of this is b minus a times d minus c, which is the length along x times the length along y that gives you the total area. Okay, you didn't have to do an integral to know this, but it helps you understanding what a double integral is. We're integrating things on a two-dimensional plane. In this case, we're integrating tiny area pieces. But now let's calculate the mass of the plate, the total mass. So once again, we have to assume that there is a density, a mass density, and let's call it now sigma, which is a function of x and y, okay? And which is measured in kilogram per meter squared. So this is the density per unit area. So if the density was constant, the total mass would simply be the area times the density, and that's the total mass. However, I'm saying that this density is changing throughout the plate. So maybe this part is heavier than this one, and it's changing smoothly, okay? So how do we calculate the total area? Well, what you can do is, let's imagine the plate again. We divide the plate into tiny bits, which have size dx times a size dy, and they have a certain mass. And this mass, we call it dm, the differential of mass. And what is the mass of this tiny bit? The mass of this tiny bit is going to be the density, which is measured in kilogram per meter squared, multiplied by dA, which is this area here, yeah? This cross-sectional area, which is equal to the density multiplied by dx times dy, because dA is equal to dx times dy, okay? Notice that units always match. So this is kilogram per meter squared. This is a surface density, yeah, the mass per unit area. And each of dx and dy, they are measured in lengths. So they are meters and meters. So when you multiply, you get something in kilograms, which is your differential of mass. So now the total mass of the plate is the double integral of dm along the surface of the plate. Okay, so we are going to add up the infinite amount of tiny elements that are infinitesimally small. That's why we are using differentials. So when you substitute dm by this, you put it here, you get that this is the integral of the density xy times dx times dy. And now you could add the limits, because the first dx applies to the first integral sign, so from a to b, and dy goes from c to d, because y goes from c to d. And that way you can calculate the total mass of a plate, okay? So I said mass, it could have been charge, the total charge. And then instead of using the mass density, I could have used the charge density, how many coulombs per meter squared, okay? And so on and so forth. Whenever we want to add something along 2 dimensions, x and y, so we are adding something on a 2-dimensional surface, then we use a double integral to add up those differentials, okay? So that is the physical interpretation of double integrals. Excellent. See you in the next video.